Statics is the study of what forces are needed to make sure that things don't move. For example, you can have three kids fighting over a cookie. All right, one kid pulling this way and one kid pulling that way. So force of kid A, here's a force of kid B. And the question is, what is the force of kid number C to ensure that the cookie doesn't move? Well, to solve for this problem over here, all you need to do is to break this down into its horizontal and vertical components. And guess what? Make sure that all the answers equal to 0. All right, so you just need to make sure your F net in the x dimension goes to 0 for whatever your calculations may be, and rinse and repeat for your F net in the y dimension. That too must also go to 0, and you need kid C to meet those conditions. All right, so you solve for those two components together, then you can solve for your FCX and your FCY, use the Pythagorean theorem towards solving its hypotenuse, and then using tan inverse or arctan to solving its angle, and then you're done. That's it. All right, but I'm going to give you a slightly different example because let's do things more challenging, and you can save the other ones for your homework as an exercise. Okay, for one thing, whenever someone injures themselves and fractures their femur, for example, when it readheres together, you want to make sure that it's of a particular length, all right? Because the muscles surrounding the femur bone tend to pull it back, and when it heals, it may make one leg shorter than the other. And as a sad joke, I guess, I usually joke to say that if it readheres that way, then you'll be walking around in circles. It's a terrible joke because in real life, you're going to have back problems, all right? You need to make sure that both of your legs are the same length so that when you walk, whether it's a straight line or in a circle, they need to be level so that your back also remains centered as well. Okay, so to ensure that your leg will readhere again at the proper length, they'll have this tensioning device towards pulling your leg so that it can readhere at the correct distance or the correct lengths. Okay, so it's a traction device. We have that picture in the PowerPoint over here, and what we want to do is that we want to represent the leg as one free body diagram. Okay, so with the leg over here, there's a couple forces acting on the leg itself. All right, first off, this is not in outer space, this is here on Earth, so the force of gravity of the leg is pulling downwards. But we also have a corresponding tension that's pulling upwards, as well as two other tensions that are pulling at a diagonal. And at the end of the day, whatever weight that we have over here supports the same weight as the leg itself. That way you're not forced to be in one confined position while you're in the hospital bed. You have a bit of mobility and freedom to move, just a little bit. Okay, and that's what the free body diagram would look like. Force of gravity going downwards, tension going in three directions. Of course, we're missing on one last thing, which is the person themselves, right? The person themselves are also providing a tension or the force in the opposite direction. All right, that's you resting on your bed while you're slowly recovering from this injury. Okay, and according to statics, all of this must net to a value of 0. Take your pick for whichever dimension you want to do first, because you'll probably have equations with unknowns, and just continue from there. Okay, I'm just going to start with F net in the y dimension, and in the y dimension for the leg itself, there are 4 forces acting on it. Okay, there is the tension going upwards, there's the force of gravity going downwards, and there are these 2 little microtensions over here as well. Luckily for us, because these microtensions are symmetrical, whatever calculation you have for them, they will mathematically subtract themselves out, as you can see when we calculate through this. Okay, so even though we might not know tension yet, we know F net y goes to 0, the mass of the leg we know, and Ty is equal to T times the cosine of theta. Where is it? Oh, did I really cut to the chase? Oh, I'm shameless. I did mathematically divide those two out. Or not divide, subtract those two out because they are the same. Alright, so tension is just equal to mg, or 45 newtons. In the x dimension, we're going to rinse and repeat. Just keep in mind that we have 2 tx's here. Let me just color code it. I got my tx here, and we have another tx here. Okay, and if we take it that towards the right is positive, then the body subtract 2tx will net to a value of 0. So the force of the body is equal to 2 of tx. T of x is equal to, as it's adjacent, the cosine of 40. So the tension of 49.05 times the cosine of 40, double it up as there's 2 going to the left. The force of the body must be pulling towards the right at 75 newtons. Okay, so we found out the tension applied to the femur. We also found out the amount of force that the body is withholding, because if the body can't sustain that, then you're going to be dragged towards the left, and that won't be fun. Okay, so torque. What exactly is torque? That's the rotational force, all right, on a particular fulcrum. All right, so that's torque. If I'm trying to use a wrench here and I'm using the wrench to, I don't know, tighten my finger for whatever crazy reason. Okay, and the torque formula is fairly straightforward. It is the force applied at the edge multiplied by the length of the arm used towards cranking. All right. Now, there are different ways of cranking. You can directly push downwards, or you can push at a diagonal, or you can try just bashing at it. And you'll notice if you try bashing at this crankshaft, you're not going to get any useful work done. All right. At 90 degrees, you get the most optimal work. Anything less than 90 degrees, it diminishes down to the point where you get to 0. And there's actually a trig function that operates that way as well. When you're exactly at 90 degrees, you're at 100% efficiency. And when you're at 0 degrees or 180, you're down to 0. And that's sine. So sine of 90 equals 1. Sine of 0 equals 0. Okay, or sine of 180 also equals 0. And that's why that's incorporated into the formula as well. So even though torque is equal to the length of the rotational arm times the force applied perpendicular to it, it's also equal to r times f times the sine of theta. Okay, so the formula on the left is the vector representation. You'll cover more of that in first year university, but in high school we'll just deal with scalar calculations. R times f times the sine of theta. Okay, as mentioned, if you're at a 90-degree angle, you'll perform the most amount of work, and anything less than 90, most amount of force applied. Less than 90 degrees, you apply less amount of force in holding an object. After all, if you try taking an object, a very heavy object, and you stretch your arm out, you'll notice that it hurts a lot holding it out this way versus you holding it close to your body. All right. Some of you guys might have been punched like that as a kid, where if you didn't do your homework, your teacher would have you hold the textbook out from your arms like this for the rest of the period. Okay. Maybe I'm one of them. You'll see in class. Okay, so what I wanted to emphasize here is that in the setup over here, our fulcrum is right here, our radial arm is right here. So the force applied looks like this. Okay, where in the example on the left, the theta would be at 90 degrees, and this one over here, we just borrow the 45. Sometimes we need to use some form of symmetry or geometry in solving it. All right, so the one on the right, according to the Z pattern, whatever angle that is inside here is the same as outside. Okay, and we'll apply that in today's lesson. So let's go through a few examples. As for this, these are short forms for when you deal with that as a vector. Okay, and just to let you know, if you want to know which way the torque is going, you just simply take your right hand, and you turn it. So in other words, if you're cranking it this way, then the vector goes towards my eyeball, and if I'm cranking it this way, then it goes towards the camera lens. Okay, but we don't need to worry about that for this course. All right, but you'll see it next year. Okay, so here's a lovely beam. All right, and here's Kelvin and Hobbes, and the question is, what is it? What is the mass of Hobbes in the setup over here? Okay, and we're going to assume that the beam is massless. All right. So a massless beam having Kelvin on one side and Hobbes being on the far end, the question is, how heavy is Hobbes? Well, in the setup over here, we're hoping that everything remains stationary or static, because that's what our topic is for today, static equilibrium. So even the torque goes to 0. So whatever torque that is on the left-hand side must be equal to the torque on the right-hand side. Okay, so whatever torque that Kelvin generates must be the same as the torque that Hobbes generates on the opposite side. Okay, so they balance out and net to a value of 0. So as for Kelvin, Kelvin's distance is known, his mass is known, and this relationship between Kelvin and the torque arm is at 90 degrees, so that goes to 1. For Hobbes, the same thing is also true. Okay, sine theta goes to 1. The length arm is known, and all we need to isolate for is the force acting on Hobbes, which also tells us the mass of Hobbes. Okay, is everything all just jumped out once? Yeah, sadly it is. Okay, so we set up our equation, And if you want, you could have gotten rid of these two right from the get-go. You'll also notice that it doesn't matter what planet you're on, those two will also divide each other out. So you're left with a fairly straightforward formula to sub all the values into and crunch it through. I'm glad I have this picture over here. Maybe some of you guys have seen these before. All right, so you can use a scale system for this, where you just simply have registration marks over here that you can use as a reference for how heavy the second panned object is. All right, so you'll notice that in some classic herbal medicine shops, they still use this technology because it works. It works really well. And one of the coolest things about it is this part right here that I'm going to highlight because I kind of erased it by accident. Where's the highlighter? Here you go. This is the neat parlor trick of it all. As long as you are on a planet, this thing will work. It doesn't matter if you're on Earth, Mars, Moon, or anywhere else. As long as there's gravity, it's guaranteed to give you the right scale ratio. All right, so you have something to compare against. So use this as your reference point. Let's say this is 100 grams. Then based upon where you place it on the stick over here, that will tell you what the corresponding mass will be. Okay, but realistically, the stick is not massless. The stick does have mass. All right, so let's say we have the setup right over here. And we're kind of curious about what the mass of the beam is, because there are times where you can set it up like that, right? Like for example, I have a beam over here and I add a little weight over here and I can bounce my hand perfectly on it and it will stay stationary because the beam is not massless. Okay, so how do we figure that out? Well, we need to follow this rule over here, which is the torque from any uniform density beam is the same as the torque generated from its center of gravity. All right, so from the beam over here, it's the same as if the beam had a weight over here. Same as what's on the right hand side. Of this 4-meter beam, it's the same as if it was a beam of no mass, but all the mass was concentrated right at 2 meters away. Okay, so this one would be at 0.5 meters away, and the other one would be at 2 meters away. And don't forget about Kelvin as well. Kelvin should be part of the equation. Okay, so the torque of Kelvin plus the torque generated by the left beam must be equal to the torque generated by the right beam. Okay. As for Kelvin's properties, we all have that. One thing that you need to do is that the radius must be divided by 2. So this radius must be 0.5, and this radius must be 2 meters. Okay. So 1 meter divided by 2, and 4 meters divided by 2. Once again, it doesn't matter what planet we're on. The outcome is still the same, so the g's divide each other out, and everything is all 90 degrees in relationship to the crank arm. Okay, so those terms divide each other out as well. So really, it's just an exercise of slowly isolating and solving for the mass of the beam. And hopefully, if you do this properly yourself at home, you'll find out that this beam has to be rather massive in order for the system to balance out. Okay, so the mass of the entire beam must be 27 kilograms, and Kelvin needs to be around 40 kilograms, and no matter what planet you're in, they'll always balance through faithfully. Here's a cute little video picture. You might have seen this before. If you take textbooks or even blocks and you start shifting them by just a slight bit, eventually you're going to get an object that is well beyond the edge of the setup. All right, and the way how you solve this problem over here is that you always make sure that the center of mass, by the way how it's set up, because you got to combine all the masses together, the center of mass is always to the left of the edge. Okay, so as long as the center of mass, when you sum them all up, is still to the left, you can have objects that hang well beyond it and be perfectly fine. Okay, one last example for the day. In this case over here, I think we're trying to look for the tension on the rope. Is that what it is? No. Oh yeah, what is the tension on the rope in this crazy setup? Okay, so this is from a textbook question. It may not be the one that we use in our class, but it was the one that was used before we bought the new textbooks. That's all. Alright, so let's go through and calculate all these things out. If you can't see the text here because it's too blurry, I just have them all given on the left over here. Okay, so these are all the given values. And now we need to go and calculate it out. So we're going to treat this as a setup where we have an arm where we assume that the mass is uniformly distributed. I know in real life it isn't, but we'll just pretend that it is. That way we can assume that the center of mass of this guy over here is placed right at the middle. All right, so if it's a 30-meter long beam, then this is 15 meters right here. And this will be the force of the crane arm. Okay, we also have the force of the payload, and the force of the payload of the bucket is equal to whatever the mass is that's given to us here as well, isn't it? Yeah, mass of the bucket, mass of the crane arm. Okay, and yeah, 30 degrees is also given to us here, and this must also be 30 degrees as well. So all we're left with is this red part over here, which is the tension of the rope that's supporting the entire system. Okay, one thing to watch out for is that the angle over here is not 30 degrees, right? As these two are complementary angles. If it's 30 degrees down here, then over here it must be 60 degrees, which I have listed over here. Okay, I think all the information is all given to you here, so go ahead, try solving for the tension. Okay, and I'll resume this video in 5 more seconds. Ready to unpause? Hope you already did. Okay, so let's get started. We know that our T net has to equal 0 newtons times meters. Okay, so whatever tension we have to the left over here must be equal to the tension on the other side of the fulcrum. It's going to be a really long equation, so I'm going to change to black just so it's easier to read. So the tension of the bucket plus the tension of the arm must be equal to the tension that's exhibited by the rope, and eventually we'll find out the force of the rope. Tension is equal to R times F times sine of theta. Capital F. There you go. This is bucket, 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 arm, 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 rope, rope, rope. I think I have this all PowerPointed out so that it'll be easier to show. Do I have it? There you go. Okay. All that stuff over here, and eventually we're just trying to look for the tension of the rope, and that's it. Okay, so yep, that's the force of gravity over here by the tension. Okay, so that's why you have the mass of the bucket times gravity. So gravity does matter in this question over here. Okay, so you sub all the values in, you carefully isolate and solve for tension, and you can find out the corresponding tension of the rope for the crane. All right, so that will be our exercise for tonight, both in the textbook and the course pack. Make sure you do the work, compare your answers with the answer key, also provided in the link. The link is found on the first PowerPoint 1.01, and I'll see you in tomorrow's episode.